Hello everybody. Today we're going to jump into some behind the scenes technical discussions about how we're making U-Boat Sim. It's been a while since I've done a technical video, and I figure for some of you that are interested in game development, you may find some of this very interesting. So picking up where I left off last time, and please go through my videos if you want to get a little bit more information about this. But basically what we have here is we have a panel for the performance visualizer. As I mentioned in the game, a lot of the underlying simulation work, such as the electrical bus, the compressed air, and a number of other systems are actually computed in parallel on background threads. So the way a normal game engine works is you have an update loop. That update loop is responsible for moving objects around and rendering them via the graphics card. That is what gives you your FPS. If you overburden that loop with too much work, you end up dropping your FPS. What you want to do, if at all possible, is to ensure that the main update loop is only focusing on rendering work. This has to do with shared memory and things I won't get into, but basically the goal here with U-Boat Sim, given the type of depth we're going for in the simulation, is very important for us to offload that work away from the main update loop and basically queue that on background jobs that are then handled by background workers. Depending on your CPU configuration, we spin up different background worker threads that are responsible for taking that work and actually processing it. Once the work is done, it gets queued back up for the main thread to pick up and to actually implement in the game. And this implementation could be, updating a dial on one of the gauges. It could be updating the physics calculations that the fixed update loop, another loop, uses to calculate rigid body physics, and so on. So if we were to jump into the game right now, you'll see, given the type of threading or coding we have going on in the system, we're actually at a pretty low utilization level. So we have a lot of headroom to grow for a lot more accuracy and a lot of systems that we're going to be working on in U-Boat Sim to simulate. You can see overall, it's on this particular CPU, and this is a pretty high-powered computer, not much work is happening in the background. So we're in a good place here to really just start adding more and more and more depth to the simulation. The AI subsystem, the Go-based AI systems runs on this, the electrical subsystem, and so on. What I also want to cover right now is you guys may have seen that we just recently announced airplanes as being one of the other in-game drivable vehicles, right? So you're able to actually spawn in a plane and fly it. In the future, we're going to add a lot more realism to the plane itself. Not to the level of detail we're going for the U-boat, right? This is not a flight sim, but enough to where it's behaving realistically, whether it's controlled by the AI autopilot or you decide to take control of the plane yourself with multiple people, right? So our vision is to have a PvP and even co-op mode where you're not the only one flying the bomber, right? You have your friends that could man the turrets, man the bombing stations and so on. So in order to do that well, we wanted to have a solid foundation that we could build off of. There are a lot of specs out there for the airplanes, and what we want to do is basically use those specs to drive the behavior of the planes in the game. So I'll go ahead and I will basically jump into it and show you guys what it looks like. So if I spawn a plane here, I'll go ahead and pause the simulation, and let's go over to the plane itself. So we'll navigate to the game object. I'll turn on gizmos so you guys can see the breakdown of the plane itself and the calculations that are happening. So under the hood, we have the mesh, which is the visual detail. This is the plane itself, and the mesh eventually, will have colliders. So when a bullet hits, when the mesh impacts the ground, we can calculate where the damage is occurring and then applying that damage to the structure of the plane itself. So visually, we have a mesh, but under the hood, a lot more is going on. So first of all, we have what we call the drag calculations. So the body drag itself of the airplane is quite complicated. And what we do is we actually use the shape of the airplane itself to create a drag calculation. So this allows us to, in real time, based on the motion, the velocity, the relative angle, all that fun stuff of the plane to the real world, we're calculating drag that the airfoil has in real time based on its shape. So that's the number one thing to understand about the flight system underneath the hood. On top of that, the aerodynamic system is comprised again of different components, and each component is simulated and acts physically upon the main rigid body. So when we have a wing here, the wing itself, if it gets damaged and part of it falls off, it will have an impact on how the plane flies, but you could still theoretically fly with a damaged wing to some extent. What we do is we model this wing based on its angle, its size, and all of the different control surfaces on it are also modeled individually. So you may have flaps here, you may have elevators at the back, the rudder, all of these are individually simulated. So again, based on real-time calculations, all of this data is fed into the framework, it's calculated in real time, and then that ends up impacting the physics engine and how the physics object behaves. So some of the things we take into account is, air density, air temperature, almost anything you'd expect a modern day aircraft simulator to take into account. We're doing that for our airplanes under the hood. In addition, we also have the airfoil itself. We're able to actually specify the type of coating the airfoil had. Was it paint? Was it aluminum? If it was, some sort of paint, was it rusted? Because that eventually may have an impact on the performance characteristics of that particular airfoil within the air. So a lot going on under the hood that you may not see to give you realistic flight characteristics of the plane. Additionally, we take into account the weight. So the weight of the pilots, as you can see here in 3D space, the weight of fuel. So as the airplane is flying and the engines are using fuel, you end up losing weight. And we do have a subsystem which allows us to specify where the fuel tanks are. So as you're siphoning gas from the fuel tanks, the weight distribution might offset the center of gravity of the plane itself. So in the future, as we build onto the simulator and perhaps add a lot more depth to each and every vehicle, such as this Sunderland Mk3, we can expose these subsystems to the player, so you'll be able to do things such as transferring fuel from one tank to another. And this can be very important. You can imagine if the U-boat flak hits you and you start losing fuel on one of your fuel tanks, you should be able to transfer the fuel to the remaining ones and be able to make it home or make it onto aircraft carrier, or in this case, land on the water and call for help, right? This is just a flying boat. On the engine side, very similar. We have, I mentioned, fuel distribution, fuel tanks, but more importantly, each and every single engine is modeled independently. So we model things such as engine performance based on known historical values. We model the performance of each propeller based on the diameter and the known characteristics. So things such as the RPM spin up of an engine is simulated as close to realistic as possible. The performance characteristics of the engine, the fuel consumption rate. Again, we're going for a simulator here. So if you're a big, flight sim fan, everything that's happening under the hood in those popular flight sims is actually going to happen under the hood for U-boat simulator. And the cool thing is that in our multiplayer mode, when you have many vehicles, so you have U-boats, you have airplanes, you have ships, all of this computation is not only occurring in the background thread locally, right, if you're in single player mode, but in multiplayer mode, we're able to basically load balance these computations across all the different computers that are participating in the simulation. So your computer will not be burdened by having to calculate 50 vehicles worth of high fidelity characteristics like we have, like some other games do. So some pretty unique implementations that allow us to scale. Again, I'm trying not to give too much away here, but you can see what we've been building in under the hood, what we've been thinking about our approach and so on. So let's actually get back to flying this thing and see how it feels. So based on what I mentioned, which is our ability to virtually recreate the different airfoils of the airplane, the drag body, the different performance characteristics of the engines, and the cargo weight and so on of the airplane, it's performing and it feels pretty realistic based on realistic accounts and some videos that we were able to see. In addition to that, we were able to add the water interaction objects to the plane. So here you can see as the plane is hitting the water, and now the water starts affecting the rigid body via physics calculations, such as a boat, you'll see how the water is getting displaced. Now you just saw a silly scene where the airplane kind of crashed on the water and nothing happened. That's because we yet haven't implemented the actual damage mechanisms, but you can see everything is in place for us to achieve that pretty soon. So the plane right now is acting like a boat would. Under the hood, the hull is displacing water. It has all of the physics calculations the U-boat has, right? So hydrodynamic forces, buoyancy forces. It's basically a boat right now because it's not moving. You can see how it's floating with the waves and so on. And as we start applying power to the engines and the wings start generating basically lift, we're able to lift off, and now we transition very smoothly into our flight model. So both flight model as well as our buoyancy plane model are working in tandem. Right now we're having lots of chaos because I did not do a good job of making sure my flaps are up, and my plane eventually in the real game would be destroyed at this point. However, let's try and see if I could take off after this mess I've made for myself. Alright, so I was able to get myself back in the air. It was a challenge, right? I had to use the flaps appropriately and all that. But I think that's the point here, right? These airplanes were not very nimble. They were flying boats. And our goal isn't to make a simple arcade game, right? We're trying to simulate realism. And these things were very difficult to fly. They were very cumbersome. And once we have the damage model there, I'll probably crash way more than I should. And I should stop using the keyboard and actually use a joystick for this, because it does require a very fine control movement. So that's under the hood, our airplane simulation. And I'll jump into some of the water physics. So about 4 years ago, I did a blog post on this that goes into details a little bit more in depth. But for a high-level review, what we do for the water physics for the lower fidelity models, such as a ship, we take the hull itself. So we take the main mesh that you see inside of the game. Once we use blueprints, we generate a high fidelity mesh that's appropriate for rendering and for visual acuity. We create a simpler mesh under the hood by taking the amount of triangles and vertices and minimizing it. And then under the hood, the simple mesh is actually used to compute in real time the different forces that would act on those triangles, right? So any triangle that ends up being above or below the water ends up being calculated in terms of hydrostatic forces. We have different wind forces and so on. And this here is an older model, which is not really representative of the quality we're going after. But just to give you an idea, this is the underlying physics mesh that we end up using. And then as this mesh is bobbing underwater, based on things such as the speed of the water, waves may be crashing into it, it may just be floating on, calm sea, we end up applying those forces to the main rigid body at the position of where those forces are occurring. So that's how you end up getting, the ship kind of in calm waters just standing still. And then when we increase the wave forces, you could see our CPU in the background starting to increase in terms of computational power, because now we're doing a lot more compute. It's still pretty minimal on a modern system. You can see how the ship starts acting to waves that are larger and larger. And you can see the results are very realistic because we're taking so many parameters into account. So in rough seas, you can see that the boat isn't just going up and down laterally. It's actually moving side to side. So we have movement in 3 axes because we have velocity or forces being pushed in 3 axes as well. So this is not static. This is not just a visual scripting mechanism. So what does that mean for the boat itself? Well, the boats are going to be pretty difficult to control. So if you want to keep your bearing, you're not just going to keep your rudder facing forward, right? As your boat is moving side to side, your direction is going to change. So you're going to have to constantly adjust your heading with your rudder based on all these different factors. And the same thing will apply to the U-boat, but it's in much higher fidelity, because we want to make sure that the U-boat gets the central attention here. This is U-boat sim. But for every other vehicle, we're adding all of this type of fidelity inside, so it feels and looks realistic, just like the main U-boat itself. So hopefully you guys appreciate where we're going with this. You can see the amount of time and effort we're spending in making sure that we're building a simulator that's as true to life as can be. The boat itself does have a center of gravity that changes with things such as the loadout, the amount of fuel, the amount of cargo. And when you end up blowing like a smokestack off of it and it ends up going in the water, for instance, it's going to affect the boat itself, even if that means it's just a slight difference. All that is being calculated in real time, and those changes are actually occurring under the hood. Eventually, when we have our complex damage model in here, it should be quite a bit of fun to see what happens to all these different vehicles and objects in the world that are being computed with realistic physics. And I do hope you guys appreciate all of this. If you have any questions for any further background tech videos like this, please let me know. We have a Discord channel. Feel free to join and put some questions on here, and when I do future videos, I'll jump into the different systems. Lastly, let's jump back to the electrical room. So you guys are probably very familiar with the electric room by now, and you probably have seen all the other update videos, but I want to kind of connect everything end to end. So when I play with this voltage regulator wheel, and you see these dials going up and down, under the hood is a very complex electrical simulation that takes into account a lot of things. As I mentioned, those calculations aren't happening frame to frame on the main thread, because that thread is only as fast as the fastest CPU core on your CPU. So if you happen to have, let's say 3.5 gigahertz, we're basically limited to 3.5 gigahertz for our rendering loop and all the heavy duty work that needs to occur for mesh translation and so on. So when you're moving this wheel, we basically queue up that calculation on a background job, and that occurs in parallel. So while the main thread is busy drawing the scene, applying lighting, applying audio effects, and so on, in the background we're taking all this input from all these different objects, we're processing them in parallel, and then when that result comes back, the main thread picks it up and applies it. In a modern system such as this one, 8, 10, 12, 14 cores, what have you, the more cores you have, the more work we can do. So theoretically, this should be very, very scalable going into the future, because we could apply more and more fidelity without incurring a penalty on the FPS side of the game, because everything is happening in the background in parallel, and we're just incurring a very small cost to marshal that data into the background frames for processing and then marshaling them back out into the game loop for rendering. So thank you for joining me today into this quick overview into some of the different mechanisms under in U-Boat Sim. And stay tuned for more update videos on the actual feature functionality of the game as we continue building it, as well as some of the behind the scenes technical developments such as this video. Thanks for watching.